Hello, welcome back. Today we're going to investigate gravity, centripetal force, motion in a straight line, and we're going to do it in slow motion. So you've all heard of the phrase, an object at rest tends to stay at rest, and an object in motion tends to stay in motion. Now these are both cases unless acted upon by an outside force. So if I throw something into space, it's going to want to go forever and ever and ever. If I have something sitting on the counter, in general it will stay there forever and ever and ever. In both cases, unless acted upon by an outside force. So I wanted to take an example everybody was familiar with. Here is just literally a power brick I've tied to this here. And I want to talk about the case when we spin this guy. So if I take it over here and spin it in circular motion like this, then it's going round and round and round and round and round. Now, the only reason it's not going in a straight line is because I'm constantly tugging on this string. I'm exerting an outside force from the string onto this thing. So theoretically, if I could cut the string when it was in the middle of doing this circular motion, if I could just cut it with scissors, then this thing should sail off in that in a direction, in some sort of constant direction, in a line, in other words. And so I want to film that in slow motion. Before we do the slow motion, let me just do it, instead of cutting the string, let me just do it by letting it go, right? So I'm going to go on the count of 3, I'm just going to let it go, and then we're going to watch it sail off in a straight line. 1, 2, 3, and here we go. Right? So you might think it's going in an arc, and that is because gravity is acting on it a little bit, but in space, it would be sailing at exactly a straight line. And also, I wasn't spinning it very fast to get a really good tension in the string because I'm a little scared of like hitting the lights over there. So what I'm going to do is film it again. We're going to do it in slow motion. I've already filmed it, so I know what happens. So I'm going to spoil a punchline for you. There's something interesting. I was trying to come up with a way to cut the string in a safe way. The first thought I had was, well, I'll just clamp a razor blade or a really sharp knife to one of my clamps, and then as I spin this thing around, I'll just bring I'll guide it in, and the string will hit the razor blade and be cut. Well, I tried that. It became very dangerous. I can't spin it fast enough to be sliced through immediately. So that was a bust. And I tried various kinds of string there, right? And I really wanted to cut the thing. So I thought, well, how can I do this? So I switched to what you saw there, which was a kite string, which is a very, very thin, I'm not sure exactly the material, but it's not plastic. It's some kind of cotton or something like that. The string is made up there, and which is very easily burned. If you put a lighter under it, it burns almost immediately. So what I did is I don't have the cylinder here, but I grabbed my torch right here and I attached the cylinder to it, set it up there, lit the torch, and then you can see in the slow motion video, I was bringing the spinning piece of string directly in the path of that torch. And I tried it several times, and every single time on the 3rd or 4th pass through the torch, it burned through and then off it goes. So that's what I did in slow motion. But as you'll see here in a minute, whenever I actually did the actual take that looked the best, what actually happened is, in that particular take, all the other takes, everything worked fine, but in that particular take, the flame didn't actually burn the string. What happened is, the string became untied from the brick itself. And so it did sail off in a straight line, but not because of my flame, it just became untied, and so you can see it fly off in a straight line. So it's kind of like, I could never have planned it like that, right? So now you know why I'm holding it up to this thing. I was trying to burn a bit of the string there to get it to sail away, but I didn't need to in the end.
Okay, here we go. You can see the brick going in circular motion. And again, I'm trying to burn a hole through the string, but right at the last minute, if you look at the end where the brick is actually tied to the string, it became untied, by total accident, and then the brick separates from the string. And notice at the point of separation that it's not curved, it goes in very, very close to a straight line. Now here I've added a straight line to show you how close the motion is to being straight. Of course, it is curved a little bit by gravity, so it's not a perfect straight line, but if you did this in outer space with no gravity, it would be exactly straight. Remember Newton, an object in motion will stay in motion unless acted upon by an outside force. Here it is a little bit more close up where you can see the string become untied and the brick flies off in a tangent line to the original circle of motion.
All right, so you can very clearly see in slow motion that it goes in a very straight line. We say that at the moment that the string is cut, it sails away on a line that is tangent to the circle. If you have a circle and a line that only touches the circle in one spot, tangent to the circle is what we say, that is the line that it follows, instantly in a straight line. And it would never ever change course unless acted upon by an outside force. But on Earth, we have gravity, we have wind, we have all kinds of things. But in space, it would literally sail away forever. So what would be a picture of this? I want to go a little bit deeper to this because we can actually understand the orbit of the planets and a few other things from this. So let's say that we have this circular motion and we have our little power brick right there. Okay. Now this power brick is connected by a string to the center, and my hand is in the center, right? And so it's moving with some velocity here, and as it moves position, the velocity is changing direction also, right? So it's going along like this. Now, the only way that I can get this thing to actually work is by exerting a tension on the string. You have to constantly be, as you're moving it around, you have to constantly be tugging to the center. So when it's here, you're tugging down with some like force. I'll just put like force. But as the thing moves over here, you're tugging this way. And so the force is going to the center. And so as it goes down here, you're tugging up. That's what you're doing when you do this motion. You're constantly tugging toward the center. You can kind of think of this as almost gravity. Gravity is pulling everything to the center of the planet, and all of the satellites in space are going in orbit around the planet, but gravity is always pulling them toward the planet. So why don't they hit the ground? Well, it's because they're going so fast horizontally that by the time you move the trajectory a little bit down, you don't move it enough to hit the ground, you move it just enough to match the curvature of the ground. And so as it goes around, you're constantly changing the direction that you're tugging, changing it from a straight line motion to a curved path in exactly the same curvature of the surface of the Earth. If you could increase gravity really quickly, then it would crash into the planet. But we launch the rocket, gravity is constant, and we give it just enough speed to be able to go around before hitting the ground, is basically the bottom line. But gravity is always pulling it toward the ground. That's why orbits are circular. Because just like with the string, if I could cut gravity off, then the satellites would all go in a straight line path away from the planet. That's what they want to do. Gravity is always on, so it's always curving it around the planet there. All right. Now, you may have heard of somebody named Sir Isaac Newton, right? And so if this thing were cut, then of course it goes off in a straight line like this, right? Tangent to the circle. You may have heard of somebody named Sir Isaac Newton. He figured out a great many things, but one of the most famous things that he figured out is by looking up at the moon. You may have heard of the apple falling and all that stuff. He looked up at the moon trying to figure out, how does the moon stay up there, right? And why does the moon move throughout the sky? And he figured out that the moon was always moving around the planet, but Earth was always pulling on the planet. And the major insight that Newton had was maybe, just maybe, the same force that pulls things to the ground on Earth extends all the way up into space. And maybe the Earth is pulling on the moon. Now, most people can't really accept how that is doing anything, because you think, just like this is going toward the ground, that if the moon is being pulled down, then it's just going to crash into the Earth. So nobody really thought that was like happening. But Newton figured out that if the force on apples or markers or whatever extends all the way into space, and if it is pulling on the moon, and if the moon is moving horizontally fast enough, then it will continue to move. It tries to move in a straight line motion, but since gravity is always pulling, it's changing the path of the motion and changing it into a circle. And he figured out, if this is the case, what does the force of gravity need to look like in order to make it do what I'm seeing, what I'm hypothesizing it to do? In other words, he said, if this force of gravity does extend all the way to the moon, and if the moon goes around in a certain speed, and if it is a certain distance away, all of which they could figure out with geometry and trigonometry back then, what does the force of gravity have to look like to make it do that, right? And he came up with what you might have figured out, Newton's law of gravitation. the force is equal to something called the gravitational constant times mass of body 1 times mass of body 2 divided by r squared, the distance between the bodies. So you could say this is the distance between the two bodies. Now, usually it's the mass of the Earth, that would be mass 1. The mass of the satellite or the moon or whatever it is would be body 2. The distance r would be the distance from the center of the Earth all the way to the moon or whatever satellite it is. And then there's a constant. We call it the gravitational constant. This force of gravity follows what we call the inverse square law, because r is not just r, it's r squared. And it turns out that the inverse square law applies to gravity, but it also applies to electricity and magnetism and the force of charges that attract or repel. It's a very similar law. Now we know nowadays that gravity isn't really a force like this. Our current theories talk about gravity either being the curvature of space-time or as a quantum effect, a quantum effect which goes way beyond the scope of this lesson. But Newton's law of gravity is perfectly good enough to get us to calculate the trajectory of astronauts to the moon, to calculate the trajectory of satellites. It's very accurate. It's probably not quite correct because we know that we have more accurate theories like Einstein's theory of gravity. But we always learn this in physics because to a very good approximation, it is very, very, very accurate. And he figured that out by looking at how things fall here and saying, what if that extends into space? What does the force of that gravity have to look like? In other words, it falls off as 1 over r squared, and it's the product of the two masses on the top. So if you make the mass of the Earth bigger, the force of the gravity gets bigger. If you make the mass of the moon bigger, then you make the force of gravity bigger. If you make the distance between them bigger, then gravity gets much smaller. And much very rapidly because it's divided by r squared. All right. Now, let me go back to one thing I said a minute ago and I glossed over it. Right? I said an object in motion tends to stay in motion unless acted upon by an outside force. Really, it should be revised. It should say something like an object in motion tends to stay in motion in a straight line, unless acted upon by an outside force. Now, the only thing I added was in a straight line business. But the reason I'm telling you this here is because I want to go a little level deeper. The point of this lesson was to show the concept of inertia, that by spinning something around with the string has a tension in it, it's pulling on the thing, and that's the only reason it's going in a circular motion. If you cut the string, or if you eliminate gravity, then the motion is going to follow a straight line trajectory, which is what Newton's laws tell us that it will do. Right? Without gravity, things move in a straight line. Without that string tugging on the path, it's going to move in a straight line. But I want to talk about what does it mean to go in a straight line, right? That sounds obvious because from here to here, that's a straight line. But you got to remember that your notion of a straight line is taught to you in geometry class a long time ago. You learned that a straight line is something governed by the Pythagorean Theorem. You learned that if you consider these all straight lines, then there's a side A and a side B and a side C. And you could put this on a coordinate system with an XY grid and all that. I don't need to do that right now, but I'm just going to draw it like this. And you learn that A squared plus B squared is equal to C squared. This is true in what we call flat space. This thing, the Pythagorean Theorem, Euclidean geometry is what it's called, that you can take the side of one triangle and the other side of a triangle and square them and add them together. And then what you get is the length of the third side squared. Equal. It's not like very, very close. It's not like pretty close. It's exactly equal. Right? But that's only true in flat space. You could consider this sheet of paper flat space. If I draw a triangle and measure how many centimeters it is and how many centimeters it is, then I can calculate to great accuracy the length of the hypotenuse of that triangle, because this, I should have said, is a right triangle with 90 degrees. The hypotenuse is the side opposite of that. That is true in flat space. This sheet of paper is flat space. But now we have theories of gravity involving warping of space and time. Einstein told us that maybe gravity is not a force like we were thinking it was, but maybe it's more of a geometric effect because space and time can be warped and changed. And I'm trying to tell you, the concept of what you think of as a straight line means that if you draw a triangle like this and you square both sides and add them together, you get the length of the third side. From one point to another, we call this a straight line. But if your space or your time is warped, maybe it's bent like this, or maybe it's a globe, like a surface of a globe. If you try to grab a surface of a globe and draw a right triangle on it, then you will figure out that a squared plus b squared is not equal to c squared on a globe. Because this equation that we are taught in school is only true for flat space. If we bend the space and then draw what we think is a right triangle, then it's not going to obey that. Now here's the part where it'll bake your noodle a little bit. Here I'm talking about space. You could probably buy it that if I bend it a little bit, then the triangle will look weird and it won't obey Pythagorean theorem anymore. But we now know that not only can space be bent like that, but time can be bent like that also. Time is different because time is the ticking, tick, tick of some sort of regular interval like a clock. Tick, tick, tick. The spacing of the ticks, that is what time is, or at least that's one definition of time. But we now know that if you travel near the speed of light in a spacecraft, then your ticking of your clock will change. Maybe it'll slow down, right? If you're near a black hole where space-time is warped very, very greatly, maybe your time will slow down. Or there'll be other cases when maybe a different flow of time can happen as well. So what I'm trying to say is that space can be bent, time can be bent. Together we call them space-time. And Einstein taught us that when a body like the Earth or the Sun is in space, it not only bends space, the coordinates of space, but it bends time. So the sheet of paper is bent around a planet, but not just the space dimensions. The time, the flow of time is different around bodies like planets and suns, but really, really warped badly around black holes, right? And so when we take an object and we say an object in motion tends to stay in motion unless acted upon by an outside force, when there's no gravity anywhere, like in deep space, and you throw something, a straight line appears to be the shortest path through space-time. What we really should say is that an object in motion tends to stay in motion along a straight line path through space-time unless acted upon by an outside force. That's what really we should say, that objects go along a straight line path through space-time. But whenever objects are in the presence of matter, space and time are warped. And so a straight line path through a curved four-dimensional space-time, where space and time are both curved, a straight line path through that might look like a curved trajectory to you. And that's why around this Earth, when we drop something, it tends to accelerate downward. Because the space-time coordinates around the planet here are not flat. They are, in other words, they don't obey this Pythagorean theorem. Because space and time, according to Einstein, in the geometric view of gravity, they do not obey the Pythagorean theorem. Now I'm simplifying a lot because in reality, you know, there's x, y, z, and there's also time, and this version of the Pythagorean theorem is a little bit different when you involve the time coordinate. But when you study relativity theory, you're going to learn about something called the SpaceTime Metric. It looks very similar to the Pythagorean theorem. It's the space coordinate squared, the time coordinate squared, and then it's equal to the metric squared. And that metric determines what does straight line look like. And if the space-time is flat, then a straight line looks like a triangle like that. But if the space-time is curved, then a straight line path through a curved space-time might look different. You know, when airplanes are flying above the surface of the Earth, which is curved, they really don't go in straight lines from a bird's eye view. They look like they take these curved, weird paths. But locally to themselves, they appear to be flying in a straight line. It's because the ground is curved. So you have to imagine not only the ground being curved, but time being curved too. And that's what things like black holes and suns do. They curve and bend the coordinate relationships between space and time. So when we take an object and we say that it should travel in a straight line distance through space-time unless acted upon by an outside force, what happens around a gravitational body is that straight line path, the shortest distance through a curved space-time, actually looks like an acceleration down. And I can't prove it to you without a bunch of math, but when you put all the math on the board, the acceleration down that we see spontaneously as a gravitational acceleration is coming about because this marker is trying to take the shortest distance through a curved space-time where space and time are both curved. Just like the airplane takes a weird-looking path across the Earth, but it actually is a straight line path across the surface of the ground. When time is warped as well, it leads to accelerations like this. And that is the Einsteinian view of what gravity is. So we started by just spinning this thing around and talking about inertia going on in a straight line. And then I took it a different direction and decided to talk a little bit about curved space-time. So get whatever you want out of this. It's fine. I just like talking about things like this, right? I mean, why should you have to wait until you're a graduate student in physics to learn about curved space-time? It's cool, right? And the nature of what a curvature is, that this is what we call, this obeys something in flat space. But if you're not in flat space, this relation is not true. That's what, and in fact, what we do in relativity theory is, however far you deviate from this relation denotes the magnitude of the curvature. In other words, the more curvature there is, then the farther away from the Pythagorean theorem looking relationship that you get, the more error there is, basically. And if you're around a black hole, the error is so high that you have these crazy effects that you can learn about, like time dilation and other things, just around a body like a black hole. And in fact, they did an experiment in the early days testing relativity theory during an eclipse, when the starlight from a distant star comes very near the sun. Like if you have like the sun right here, and then way far away is another star, right? The starlight, normally grazes the surface, and maybe here's the Earth or whatever, right? And you have some kind of observer like this, right? So if the sun is not here, and if the sun is here, it's going to influence the path of the starlight. And so what they did is they knew what the sky should look like. They knew what the constellations should look like in the nighttime when there's no sun there. And then when the sun got covered up by the moon, all the stars come out, and they look at all the positions of the stars surrounding the sun, and they figured out that they were shifted, very, very precisely calculated by the amount of curving of space-time actually curves the trajectory of starlight coming in. And so it's not where, it doesn't appear to be, the constellations look different around the edge of the sun during an eclipse as compared to when there's no sun there at all, because the starlight is bending. And that is something that wouldn't have been predicted by regular gravity, because we all know that sunlight or any photon, it doesn't have any mass. So when you go back and look at Newton's law, you have to have some mass of the Earth, mass of a photon, but a photon has no mass. It should not be influenced by gravity, but it is. And that's because our ideas of gravity are a little more complicated than Newton's ideas. And the Einsteinian version of gravity probably isn't totally correct either, because it does not include quantum mechanics, but it's a lot more accurate than the Newtonian version. All right, so let me know what you think. Did I go too far in the weeds? Was it too far out there? Would you rather me just focus on the experiment, talk about it, and be done? That's fine, just let me know. Give me your thoughts, please. I'll follow you along. I'll see you in the next one.
Learn anything at mathandscience.com.